Okay, guys, today what we're going to do is we're going to take a look at how we can use calculus to determine turning points. So, we looked at turning points when we were looking at those parabolas, right? The turning point was the vertex, where it stopped going down and started going up, or stopped going up and started going down, right? Well, those points have special values. If it happens to be going up and then starting going down, then that top point, that vertex point, is called a maximum. If it's going down and then starts going up, that bottom point, the vertex, is called a minimum. And we can use calculus to determine maximums and minimums really easily. Okay? Because we know that at those turning points where it's changing, where it's no longer going up and it starts going down, but it turns and it's going down, and vice versa on the bottom, we know that the slope of the tangent line right there, that tangent line is going to be completely horizontal. And what is the slope of a horizontal line? 0. Right? Right? It's the slope of a horizontal line. It doesn't go up or down any. Right? So that means the slope is 0. Well, we can use that information to be able to determine if something is a maximum or is a minimum, etc. And you're going to see a lot of this when we start doing the application type problems. For example, a business wants to maximize profits and minimize what? Costs, right? Okay. Losses or costs, period. Yeah. So you're going to see a lot of max-min type problems. And there are a couple of ways that you can use max-min. Now, we're going to start off slow, and then I'm going to show you one that you're going to go, why didn't you show me that in the first place? Because it's so much easier. But it doesn't always work. So you have to see the one that always works, and then you see the shortcut that works most of the time, but not always. Okay? So if you already know something about what it is we're doing, don't just say, there's a better way, an easier way to do this, Mr. Self. Because I know there is. But it doesn't always work, and this one always does. Okay? So that's why you have to know it. Is that a good enough reason? Yeah. I hope so. Good. All right, so here we go. Let's look at some turning points. Okay? So we're going to be looking at increasing and decreasing functions. Remember that these are always read from left to right, just like words on a book, right? So even though, if you look at this line, the arrow is pointing down, in reality, that's an increasing line because the numbers are getting bigger, right, as you go from left to right. Now this one clearly is decreasing, and the arrow even looks like it's decreasing, right? So be careful about those arrows. Don't just look at the arrow, see it's pointing down, and say that's decreasing. Read it from left to right, just like you're reading words on a book. Okay? All right. Now, so a function is increasing where the gradient is positive, right? We know that from our study of gradient or slope. If the slope is positive, that means the line is going up or increasing. And it's decreasing where the gradient is negative. Make sense? Remember that from just anything you learned about slope. Where it changes from one to the other, we get what's called a turning point. And turning points may be either maxima or minima. Maximums or minimums, right? Depending on, is it increasing, then decreasing? What would that be? Increasing, yeah, there you go, maximum. If it's decreasing, then increasing, that's a minimum. Okay? So you know things about this. I just might not have put it together in quite this way before. Right? Now, so what we're going to do is we're first going to have to locate those turning points. But again, because we know something about the slope at the turning point, that makes the mathematics of it really easy. Because in order for it to be a turning point, that's where the tangent line is a horizontal line, which means that the slope has to equal what thing? 0. So if we set the slope equal to 0, we can find that point easy. Does that make sense? Okay? All right, so we can use this to calculate the the coordinates. So let's look at an example here. Calculate the coordinates of the turning point of the curve, and then they give you a function to determine its nature. If you look at this function, the highest exponent it is at what? 2. That means that the degree of it, remember the highest exponent is also known as the degree. The degree of it is a 2, which means it's a quadratic function. And the graph of a quadratic function is always a what shape? Parabola, either opening up or opening down. And how can I tell if a parabola is opening up or down? The sign of that x squared. Okay? If it's positive, then that means it's opening up. If the sign of that x squared is negative, then it's opening down. Remember that from our algebra? Okay? Now, in this case, it's positive. That means it's definitely opening upwards. Therefore, we are looking not for a maximum, but a minimum. Right? So just from our basic knowledge of what these things do, the parent graphs, what these things look like and how they behave, we already know a lot of information. Right? Now what we have to do is be able to find what those coordinates are. Okay? And we'll write down the steps. We'll look at this example and then we'll write down some steps for it, okay? I'll just get rid of my marks on there. All right. So, the first step is to simply differentiate. We're looking for a slope, and in calculus, looking for a slope always means differentiate, right? Because the differential, okay, is the slope. So first thing was we'll take the derivative, is what I call it, but they call it differentiate. Take the derivative. Again, remember the derivative. Multiply the exponent times the coefficient. Subtract 1 from the exponent. It's been a while. So here, 2 times 3 gives me 6. 2 minus 1 gives me x to the first. So that's where they get the 6x. 18x, that's a 1. 1 times positive 18 is 18. X to the 1 minus 1 is x to the 0, which becomes a 1. In other words, it just disappears, right? And then finally, the derivative of any number term or any constant, we call them constants, sorry. Any constant is 0, right? And since it is 0, we don't need it. Don't think it just goes away. It makes a 0, but we don't need to write plus 0. That's why it looks like it goes away. But don't think that it just disappears, right? So now that we have our function, our derivative, our f prime of x, then what we can do is calculate the x coordinate. We need an x value and a y value for any point. Remember, any point on the graph always has an x and a y. Not just one or the other, but both. And we already know that at that turning point, m equals what thing? What number? 0. So all we're going to do is replace f of x with 0. Now, I don't know why they decided they think that they need to put the 0 on the other end. It doesn't matter. You could just have easily written, because it was f prime of x, right? Equals, you could have put the 0 there and then 6x plus 18. It doesn't matter. They reverse it and put the 0 on the other side. I guess it just makes it more beautiful. I don't know. Then they solved it, which gives you x equals negative 3. Again, remember solving, just get the x by itself by moving anything away, any terms that are added or subtracted from it. And then divide by the coefficient to get your x completely by itself, right? Okay. Sorry, I'm always doing that. I just assume y'all want to see all of it. Okay. There you go. So now we have it. Now we have the x value. If I know the x value, how can I find the y value? Substitute in. Okay, so I'm going to simply put everywhere there's an x, I'm going to put negative 3. And if you look, that's what they've done here. They put in negative 3 in place of all of the x's. In the derivative? No, in the original function. And again, we'll write some notes down so that you can and remind you of those pieces. Okay. They're just assuming you remember. So in the original function, and that gives us f of x, which means y, right? So y equals negative 28. That means it has a turning point where x is negative 3 and y is negative 28. We know it should be negative. Why? Because it's going down, right? Okay. And if it has zeros and the vertex is going to be below the x-axis, that means that it's going to be one of them is going to be negative. The y value at least is going to be negative. The x value could have been positive, but it has to be below that x-axis. Because if it was above the x-axis, that means it would have how many real zeros? None. They'd be undefined. Okay? All right. Sorry, I was sneaking a little extra in there. Okay. So now, what we need to do is we need to determine the nature of the turning point. And by that, when they say nature of a turning point, they mean, is it a max or a min? Okay? So that's what nature of the turning point means to find. So we're going to be looking at finding the nature of the turning point. So you have your points. We just simply calculate the gradient on both sides of that thing. Now again, this involves a little more work than the method we're going to see later, but this method always works where the other method doesn't always work. Okay? So they unfortunately do not tell you why they picked -4 and -2, but what was our vertex, in other words, our axis of symmetry? X equals -3, right? So all they did was pick the two closest integers to it. Not whole numbers, sorry. Two closest integers to it. You could have easily used 3.5, -3.5 and -2.5, but you don't want to do that. So pick numbers that make sense for you. All right? But you would need two values, one on either side. Then simply calculate the gradient to the left and then calculate the gradient to the right. Well, if we're using gradient, does that mean the original function? No, we're plugging into the derivative. Remember, anytime it's gradient, that means you're plugging into the derivative. If you're looking for y, that's f of x, the original function. If you're looking at m, that's always f prime of x. Just remember, always keep that in mind, right? So we just plug those values in place of x into our gradient, and we see that, okay? And we don't even need the numbers. You only need the signs, okay? If it's negative, then it's a decreasing function. The slope is negative, that means it's going down. Doesn't make sense? Okay? If it's positive, that means it's an increasing function. The line is going up. So, if it's negative, then positive, that means down, then back up. So, therefore, a what? Minimum. Okay? And you'll learn later that that's a local minimum. We can't be, but in this particular case, we can be sure that this is an absolute minimum because this is a parabola. Can it go down anymore? It's going to go down to a certain point and then go up for the rest of its life, right? So there's only one minimum, so it is an absolute minimum. Can't get any lower. But if you had a curve that was doing this business all over the place, can you be sure that that one is the lowest minimum? No, so that's why it's called a local minimum until you prove that it's an absolute minimum, which we will talk about later. Yes?
How do you know which one comes first? Doesn't the negative always come first?
Pardon me?
Don't the negative always come first?
No. When you plug it in, depending on the signs of the function that you start with, right? Now, in this case, the negative is always going to come first because it's a simple parabola going down, right? But you read it so you always put this one first and this one first. And so the -4 gave you the negative value. But notice -2 gave us a positive value, right? So you put those numbers in from left to right. So the one you picked on the left is going to tell you the first value. The one you picked for the right is going to be the second one. Does that make it more clear?
Yeah.
And but you know that from this parabola that's what's happening, right? Okay? It's good. But they're giving you a simple function to start with just so you can really see what's happening. Okay? So if it's negative, then positive, that means that it's going up. Okay? Goes down, then up. So that makes it a minimum. Okay? Looks good? All right. Let's look at this example. Calculate the coordinates of the turning points of the curve. And again, the steps for doing this are always the same. So let's just write out some steps really quickly. Get some paper. To find the minimum or maximum. And this is called using the first derivative. Because how many times did we take the derivative? Once. But we can take the derivative of the derivative, which would mean wouldn't be the first derivative, and then we could take the derivative of that, which would be the third. And you're going to do all of those. It just gets easier and easier as you go, though. Trust me. All right. So first, take the derivative of f of x. Okay? Second, substitute 0 in place of f of x and solve for x. Make sense? Okay. Third, substitute that x value into, f prime of x, Put the prime on there. Would you guys make sure I do this right? Did you write the prime on there and just not tell me?
I was going to tell you once you finish writing this.
No, you tell me when I'm doing it. Okay. All right. Substitute that x value into f of x. Now be careful. You're substituting 0 in place of the function value after you take the derivative. So the derivative, because you want to find out where the slope is 0. But now I'm looking for a value, a function value. That means I go back to the original function. Okay? And solve to find y. It cracks me up. I look at Ella and she's like, all right. Okay? Then find test points. One on the left, one on the right. Okay? So we'll know our value, and most books also tell you to just draw a line on the axis of symmetry, right? Which is always the x value, no matter what kind of function you have along that x value, so that you can see which one's the right or the left. But they just mean right or left of the turning point, right? Then substitute those into f prime of x. Because again, we're talking about slope here. Anytime you're talking about slope, you're going to be using the derivative. Anytime you're talking about x and y values, you're going to be using the function. Okay? If negative, then it's decreasing. Which makes perfect sense, right? If positive, then it's what? Increasing. And that will tell you, increasing, decreasing, what's happening on either side will tell you, is it a maximum or a minimum? Now with parabolas, you can tell automatically, right? You know which way they're going. But when you start getting more complex functions where they start moving up and down a lot, it's difficult to tell which one's which, right? You know, one of them's a maximum, one of them's a minimum, but you don't know which is which. Okay? All right. So let's use those directions now and look at that example.
There's really cheeky. So if it mentions the gradient, like in the question, asks you to find it or use it, it's always
The derivative. You bet. Yep. Anytime you hear slope, think derivative. Okay, so here we go. We have our function f of x equals 3x squared. Oops, I'm sorry, that's the one we just got through doing. Don't want to do that one again. F of x equals x to the third minus 3x squared minus 9x plus 11. We want to find the turning points and determine their nature. Are they maximum or minimum? Well, the first thing we need to do is do the derivative. Right? Because we're going to be finding those turning points. That means we need to know the slope. So f prime of x equals 3 times 1 is 3. X to the 3 minus 1 is 3x squared. 2 times negative 3 is negative 6. X to the 2 minus 1 is x to the first. 1 times negative 9 is negative 9. X to the 1 minus 1 is 1, so we don't need it. And the derivative of any constant is 0, and we don't need to write the 0 in this place, in this point, because we have lots of other stuff going on, right? Now, what we'll do is solve for x. When f prime of x equals what number? 0. Because we want to know those turning points. So we'll put in 0 in place of the x prime. 3x squared minus 6x minus 9. This is the example, the second example. Yeah, it's not one of the ones from the homework. It's the second example. Now, this one, quadratic equation. So we'll solve it. We'll try to solve it by factorizing. First thing you notice is 3, 6, and 9 will all divide by 3. If there is a common factor, divide it out first because it will make your numbers smaller. I can also just simply discard that 3 because later when I set 3 equal to 0, does that make any sense? No. So if your common factor is a number, you're always welcome just to throw it out. But if your common factor was an x, could you throw it out? No, it would give you another solution. Okay? Because x can equal 0, but 3 can't equal 0. Now, well, if you set it equal to 0 later, you get 3 equals 0. Is that true?
No, but how do you even get that in the first place? Because,
well, when you...
how does that exist?
Okay, well, let's just leave it for a moment and I'll show you. All right? X squared can only be x and x. I'm looking for the two factors of negative 3 that combine to make negative 2. They are 1 and 3 if the 3 is negative and the 1 is positive. Yes? Now what I need to do is set each one of those factors equal to 0. Right? What is the first factor? Which doesn't happen. Right? But if your common factor had been an x squared, if that had been an x right there, and I put x equals 0, would that be okay? Yeah, that's how that happens. Okay, but in this case, it was a number, so who cares? You could have thrown it out. All right. Then x plus 1 equals 0. You show as much or as little as this as you need. I will always show every step of the process, but that does not mean you have to. Subtract 1 from both sides gives us x equals negative 1. Add 3 to both sides gives us x equals positive 3. Those are my two x values. Now, those are the x values for the turning points. And I knew there were going to be two turning points because the highest exponent was a 3, so this is a cubic equation. And the graph of a cubic is it goes up, it goes down, right? Or it goes down, then goes back up. We don't know which one. Well, we really do because the first term is positive. It's going to go up, down. That's okay. So now, putting those two into the original function, substitute into f of x, not your derivative, but we're looking for a number now, a number value now, a y value. So plug those into the original function. Okay. And we have two of them. That means we're going to have to do it twice. So f of negative 1 equals negative 1 cubed minus 3 times negative 1 squared minus 9 times negative 1 plus 11. Okay? Think we can do that all on one line? Don't know. Negative 1 cubed, negative 1 times negative 1 times negative 1 is still negative 1. Negative 1 squared is 1 times negative 3 is negative 3. Negative 9 times negative 1 is positive 9 plus 11 is going to give us negative 4 plus 9 is 5 plus 11 is 16. So for that particular x value, our y value is 16. So the first turning point is negative 1 comma positive 16. Okay? Now let's do the same thing for the second turning point. F of 3 equals 3 to the third power minus 3 times 3 to the second power minus 9 times 3 plus 11. Sorry, it's getting a little messy. Which gives us 3 to the third power is 27. 9 times negative 3 is negative 27. That's nice. All right. Negative 9 times 3 is negative. Do I have that right? Yeah. Okay. Negative is another negative 27 plus 11. Those two are going to go away. Gives us negative 16. Do not think that that's always going to happen. All right? Generally. But not always. Okay. There we go. So now we have our other turning point, which is the point 3 comma negative 16. We good? Now, we need to find test points on either side of those. And so if we have negative 1, think about the graph. If you have negative 1, that's right there. So we can use negative 2 and 0. And then 3 is over here. So we can use 4. And I'm also going to use 0. It's not right next to it, but isn't it to the left of it?
Yeah.
If you can use 0 as one of your numbers, use it. It doesn't matter how far away it is, use it. Okay? As long as it's between the two values, you can still use it. Okay? Because 0 is going to make your life a lot easier.
So it doesn't have to be between the two.
It doesn't have to be right next to it.
But it can't be like negative 4.
Right.
Because
it's on the past the other side. Okay? All right? So think about the graph. Okay, you have negative 1 here, positive 3 there. I need to pick any number that's over here, any number that's between them, any number that's there. Okay? Doesn't matter.
But if you only had just like a
Are you okay?